So welcome again, this time in the afternoon session. It seems like I'm in all the sessions today. What I'm talking about now is Cocotb, and I will talk about that as a person that has been using and is currently maintaining Cocotb. And essentially, I will tell you a bit about what is Cocotb and what happened since essentially the couple last year at least. So we should start off with two statements that is verification if you do it software, and if you do write software, it's actually a good idea to write software in a software language. And with Cocotb, you can do verification in a software language. In this case, you can do it with Python. So we have many people mocking the name Cocotb. It wasn't my invention, but there is also not clear what it is. And since we had the IBEX yesterday, I think Cocotb is a parrot, and it's coming from a German comedian that has this very funny joke about this parrot sitting on his shoulders, and it's called Coco. And I think it's a parrot, but the thing is, it's not a scary parrot, so it won't scare your favorite cats. And this time it could be UVM, so it's all good, so you can use it. So that out of the way, what actually is Cocotb? First of all, I think the easiest way to put it, it's a simulator plugin for your RTL, digital design simulator. And it is a Python library that allows you to write code with that simulator to actually simulate designs. In more block style, in block drawings, and you've seen my drawing skills before. You start with your RTL code, be it in System, Verilog, be in VHDL, whatever your simulator supports, that's fine. You run that in your standard RTL simulator. Can be any industry standard simulator, can be an open source version, can be any of the big three. So it's Icarus, GHDL for the two main open source options, VCS, Model Sim, NC Sim, whatever you have. And on the other side, you have your test bench. That's what you want to do in the end, that you want to do verification. So you have your test bench, you have your whole setup. You write that in Python. Now, of course, you're missing two things. How are we able to have those two blocks talk to each other? And that's the first thing that Cocotb provides, is a link between the RTL simulator and your test bench in Python. And this link works, and that's why it works in typically all RTL simulators, by using the VPI, FLI, or VHPI interfaces. So that's a standardized interface to talk to your simulator, and reading signals, setting signals, all that kind of things. So they are actually implemented by all simulators that we have out there. And on top of that, we have a part that is the Cocotb library, and you'll see that in action in a bit. The question that comes up repeatedly, and of course it's no definite answer for that, but why should we use Python for verification tasks? And the quick answer, I think, was what I gave before, because it's software and it makes sense to write it as it is software. And if you go for an established software ecosystem, Python is a very obvious choice. It's not the only choice. It's productive to write. It's easy to read. Code is mostly read. It's easy to interface with, and we'll see a couple examples later on. There's a huge existing ecosystem. So all stuff we have been talking about, how do we do package management for RTL code, things like that. You have to reinvent all those things actually if you do, for example, UVM-based verification. Just drop in a bus monitor or something like that on a UVM-based simulation environment. So you're back into the package manager discussion. All that stuff has been solved for software environments. In this case, it's there for Python. It's an interpreted language, so you can leave your simulator open, change the test bench, just press F5 in most simulators, and you get your updated test runs. You see typically the waveforms in VCS or other simulators like that. And it's a very popular language. It's easy to find engineers that are fluent in Python that have used it before. And we are currently, as a company that's on a low-risk side, we're trying to hire a UVM engineer. And it turns out it's surprisingly hard to find a UVM engineer, at least in Britain. So this is a major helping point to get actually people into your code base. The thing that's not mentioned here, and that goes back to that slide, is if you go for UVM, you need to have a commercial simulator because there is no simulator out there, or kind of proprietary simulator. There is no simulator that actually can run UVM code that is freely available. Going back to the situation that you want to actually have more people doing tests and writing tests and verification for your code, with Cocotb you can use Icarus, you can use GHDL. If you run in a subset that Icarus, a Verilog subset that Icarus supports, you're fully set and done. If you write VHDL, GHDL has a very, very good language support for even the most recent VHDL options. So it's all set. That's good, so you can run that in Travis CI without any license problems at all. So what am I going to do in this talk? First of all, I will give a quick Cocotb teaser, and that will be a very, very brief introduction, just to show a couple syntax things. I will do 2 showcase examples of things you can do with Cocotb, and I will give a quick project update later on. I won't go into any implementation details of Cocotb. Ask me if there are questions on that. I think before we start there is how many people have heard of Cocotb before? Just raise your hand. That's the majority, that's good. How many have used it? How many have used it in actually a kind of larger project? That's good. Great. So we'll keep the introduction short and go a bit on the update side more. First of all, why am I here presenting Cocotb? I'm Philipp, as you have seen before. I have a lot of hats. I don't know how that would look in reality, kind of having multiple hats stacked on top of each other. But here, what I'm doing is I've been with the WOSH Foundation for a long time. We have been in contact with the Cocotb guys, that's Stu and Chris, that essentially invented and first started Cocotb for a long time. And essentially, if you looked at Cocotb a couple of years ago, it looked very silent, at least. So most of the stuff that needed to be done is there is an existing community, and there wasn't that much effort put into kind of maintaining that, merging patches, things like that. So essentially, they asked us at the WOSH Foundation, can we actually help out? And in the end, it was me that took over and mostly doing maintenance work there. It's not that much coding, but it's a lot of reviewing, merging, making sure that people are actually able to work together and get Cocotb moving forward. So that's why I'm here today. And I'm working at low risk. We're actually hiring. So if you want to do Cocotb in a commercial environment, maybe that's something we can do. Okay. For those of you that do not know Cocotb, and the other ones, maybe it's a refresher. We start with a very simple device on the test. In this case, it's a FIFO. I'm not going to show the implementation, but trust me, it's a FIFO, and it has a very standard interface. You want to write a test for that, and our first test, and that just introduces a very kind of small set of language features, is let's just generate a clock for that test case. And in this case, we have the first piece of, oh, I'm going to annoy Simon here by moving around. You have a standard Python function, and you annotate that with @cocotb.test. So that indicates, oh, this is a test. Then what we do is we get past this device on a test object, and through that object, you have access to the full hierarchy of signals and ports. So you just access them as if they would be just attributes or properties in a Python object. And you can go down the hierarchy however deep you want. What this is, it's just a reference to this clock object, and you can assign it to other variables as well, pass it around, just as you would expect things to happen. Now let's generate a clock. So we set this clock signal to 1. We wait for 1 nanosecond. We said it's a 0, wait for a nanosecond again. So we get a 2 nanosecond clock there. Now you might be wondering, does smaller equal looks like hardware, but it doesn't look like Python. And that's, in fact, that's the first addition that Cocotb makes, and that's part of this Cocotb library. Essentially, your shorthand for we assign this clock here a new binary value object of, and pass it a value 1. Binary object is also one of those things that Cocotb provides. It's essentially a wrapper around ways to assign 4-state logic. You want to assign access to signals as well, for example, and that's, and allowing you to pass those to the signals. Now, to actually get this running in Cocotb, we need one more thing. We need a small makefile. And this makefile is helped by Cocotb having a set of kind of included makefiles that are already there, and you just specify the top level, that's the RTL code, and the module that you want to have, and you include those standard makefiles, and that's about it. Now, that's the full installation instructions of Cocotb as of a couple months ago. You install it from pip, you run your makefile. In this case, we run it with Icarus, and then it runs, and I'll show you the output in a second, and in the end, you can dump the waveforms that we got. The nice thing is, that's why I kind of have here, so it runs with Python 2 and Python 3, whatever you prefer. If you run with Python 3, you just need to make sure that you kind of actually pass this binary name to the makefile. Good, so how does the output look? Standard test, so we have this single test, just runs there, and we get the speed and all that stuff, output. And if you look at the waveforms, it's a clock, it's amazing. Good. This was to introduce some of the very trivial syntax features, but of course, we need to get started somewhere. Now, hardware is all about parallel, doing things in parallel. And how do you do that in Cocotb? It's through coroutines, and that's also where the name comes from. It's coroutine-based test benches. And the first coroutine that we look at is we want to actually generate this clock in parallel to all our other code that runs. So we have a clock here, a clock object. We say this is the clock port that we're using. We go for 1 nanosecond of period in this case. We start the clock and we fork off this coroutine, so it runs now in the background, parallel to everything else. What do we do next? Is we're still with our FIFO example, so just let's make it a bit more elaborate. We set a couple values, that's the D import, the write enable, the read enable, all that stuff, set it to 0, have a reset, wait a couple cycles, set the reset to 0. Standard initialization, nothing amazing here. Now, we do the most trivial and boring thing you can do in a FIFO is just write a single word and read a single word. And again, that's not the final state, but it's a starting point. What do we do here? We set a value to input, set the write enable, wait a cycle to make it actually go on the next cycle in, and then we wait until the FIFO is not empty anymore, it's just getting around the latency, and then in the end, we have here, where are we? There we are. We read out the value and make sure that it actually matches 40 to what we wrote in there. The thing is, now, first we said that all those objects you access under DOT are references. If you want to get the value out of that, just add .value, and that's it. Now, of course, writing a single word and reading a single word is not where you want to end up with. What you will do is have a write and a read thread at one point in time to just fork those off as normal coroutines. And I'm just showing that example quickly here. So we have a write coroutine, a read coroutine, and once you have finished, whatever that means, after a couple thousand cycles, after a given time, after you've kind of fulfilled a certain number of patterns that you want to push through the FIFO, you have those coroutines join again, and that's it. Now we have seen a lot of calling of coroutines. How do you actually write them? Trivial as that, just annotate your function with a cocotb.coroutine, and then you have normal Python code in there. You can just have kind of being executed in parallel to everything else. We can return from those coroutines, you can return values from those coroutines, or you can have them just running for a specific amount of time until you've, for example, done 1,000 cycles, and then just kind of have them join later on. So that's a very trivial, basic introduction into what Cocotb has, but it's essentially all that you need to know in terms of making this a successful starting point for your own test benches. You don't need to add that much to Python to actually be able to interface with the simulator and do useful things. And that's also what Cocotb is all about. So it's a kind of minimal set of building blocks, but building blocks are pretty robust and get you started quickly, and just make sure that you actually, all the stuff you know from Python, how to write software there, how to do coding there, you just can take that over. What can you do with that? We said kind of Python is a very established language, and you can now tap in the whole ecosystem that you have. And that is just code somebody posted on the chat, I think 2 or 3 days ago. You have your golden model of whatever algorithm that runs in Matlab. That is not an uncommon thing to have. Matlab has Python bindings. So there is actually, if you go here, you go to the Matlab engine for Python, you download that, and you just have those new features there. You import the Matlab engine, and you can start it, so it runs Matlab in the background. Now what you do is, actually, you have your device under test, run that, feed, for example, input data to it that you get from a Matlab model, or the other way around, just let it compute something and get the results back and compare them to the Matlab golden reference model. All that is trivially done in those couple lines of code, so there's nothing more you need to do. Another colleague of mine was doing a lot of package processing in Ethernet packages. And of course, if you want to run tests on those, you typically are given trace files, pcap files, whatever you have, or the Ethernet traces. You want to feed them to your simulation. Would it be nice to just have an existing library that is able to parse those pcap files, kind of add, modify them in some way, and then just pass them into a AXI bus or whatever you have in your existing design? So this Python library exists. The ScarPy library allows you to read and write pcap files, and you can then, of course, watch them in Wireshark or all the other tools that are there. So essentially, that's what I meant. You tap into existing ecosystem. And what he did, and that's a very, very short part, kind of a snippet of the code that he had, is essentially you have the coroutine here, read the packets. They're coming from the pcap file that has been read. But in the end, what you do is just convert them into an AXI packet and then compare them to whatever you had before. So that's the power of having Python, the power of having a full ecosystem. Just tap into that. With that being said, let's have a very quick look at what happened to Cocotb. I think we shared most about the history before, so that's essentially where we are at now. It's stable, and we have now a shared maintenance model to make sure that we are able to scale that, not scale, but scale that task up. What are the future plans? We want to have more well-documented extension vectors. We have had a lot of code that was developed in internal repositories. We want to make sure that people are actually able to build on top of that. So that needs better extension vectors. Just do a pip install, whatever, AXI bus monitor extension, and be done. And we need a better build system support. The makefiles that we have today are working very, very well on Linux and Mac-based operating systems. They're not that great on Windows, and we have a lot of people that actually want to use Cocotb and simulators on Windows. So there we're looking for a better alternative. It turns out most of the alternatives are not actually really that compelling. So if you have input in that kind of domain, that would be fantastic to have. One other future plan, and I see, where is Michael? I saw him before. We have the best working open source simulator for System Verilog today is Verilator, at least in terms of the language features that it supports. Wouldn't it be nice to actually have Verilator running and have Cocotb interfacing with Verilator? That's a non-trivial task, unfortunately, since Verilator is one of those simulators that does not have a full VPI interface. There is currently effort to add that back to Verilator. And the funny thing is, there has been talk about Verilator and Cocotb for quite some time, and it turns out there have been multiple people that had essentially the code laying around in a non-cleaned up fashion. So I had one that essentially took a couple days to write. Stefan Valentowitz had one. There were another guy in the US working for a company that had their code laying around. So now we're finally in a position to actually get that stuff together and get it upstreamed. So there's still a lot of work, but we're getting there. Just let me know or let Stefan know if you want to join that effort. With that being said, Cocotb is ready. Just install it today best. It's of course always the best. There's a mailing list. There is the code on the web, and the code links to document. The web links to the documentation. Getting there, and the code is there as well. Thanks for your attention.
Okay. Any questions? By the way, the person that is making fun of the name that Philipp was referring is me. If you want to position they hate, that would be me.
No, not the hatred. It forced me to think about a mascot. That's the perfect service you did to the community.
Okay, I think if
Jonathan
asks question every time. Okay.
So obviously MATLAB isn't open source. There's a very similar package called Octave, which is. Does Cocotb support that? Or would it be advantageous to FOSSi to support it?
I must say, kind of the code I showed here was kind of posting on the chat a couple days ago. I have neither played a lot with Matlab recently nor with Octave, so I don't know their story about current Python bindings. But if they have, as you say, kind of Python bindings that would work in a similar way, it's very easy to do. Otherwise, I think there are a sufficient amount of ways to call Octave and get results back. The worst case, just through command line options. But yeah, okay. So answer is yes, it's there. Should work.